Hi everybody and welcome to another video. For those of you who are following my channel since a few months or so, it may be a little bit confusing about this very long video today, but stay with me. These are my lectures I am trying to create and upload here on YouTube that I was giving in the university now for the students. And a lecture takes around 90 minutes. So this is the very first one. So let's hope it is really 90 minutes or not longer or shorter. Now, the other thing is also this video is also for the students. Yeah, so if you guys did not understand certain parts or you want to have a certain recap of certain concepts, then this video is also for you. So you can click through it. There are some timestamps I provide, maybe for 90 minutes, not that many timestamps, but yeah, let's see. I will create also a playlist where also the next sessions will also be uploaded there. I'm currently planning also a larger session in the next semester and also sometimes uploading my own content from older lectures or so about scientific topics. Now the other channel's content, like for example the coding part and so on, they will of course remain. This is just an additional thing for everybody who's interested in certain concepts that are being taught in the university, or as I said, as a recap of the old lectures. Now, today's session is about NASA's SPICE toolkit. And I would assume that SPICE is probably one of the oldest toolkits out there, or one of the oldest software we have. And it even dates back to the Apollo times. Well, the software was not there created, but during the Apollo times, there was a certain need identified, the need to understand the movement, the orientation, the pointing, and everything else that is somehow related to spacecraft missions, planetary movement in the solar system. And SPICE was created by NASA and is also completely open source and can be freely used by anybody to tackle this problem. But before I spoil too much from the actual lecture, I would suggest we are switching now to the slides and we are going through the presentation. And in the next video, we will have a live coding session. Yeah, and this live coding session, I will talk a little bit about later. So let's go, let's dive into the slides and enjoy. So welcome to this short lecture. And today, as I already mentioned beforehand, we are going to talk about the SPICE NASA toolkit. So the outlook of today's presentation is that first of all, we will get an understanding of SPICE in a nutshell, and then also the requirement, why do we need SPICE at all? Why has it been created? By taking a look at the science planning and also science operations, especially with an instrument that was created or built by the Cosmic Dust Group, namely the Cosmic Dust Analyzer, short CDA. Afterwards, we will cover the fundamentals of SPICE, like the fundaments, the kernels, and also the toolkit itself. The point is, though, that SPICE is a very comprehensive and it's a large toolkit, so we cannot cover everything in 90 minutes. It would probably be more like, an entire semester of lectures to cover all the topics. Now back to the YouTube video or the channel, there are also other videos and also code in the past that were based on SPICE, so additional content is being provided in the GitHub repository that you find in the description of the video. First of all, I would say we dive into the SPICE in a nutshell thing. And first of all, we need to know how it was created. And as I said, it went back to the 80s around where some first preliminary work has been conducted because it was identified that somebody or one needs a ground truth for data, especially for the spacecraft missions on the science planning operations analysis. Otherwise, you have maybe ambiguous results and you don't know really why. So if you have for certain in certain data analytic topics or plannings a ground truth everybody can rely on, then you have especially results that are reproducible. Of course, everybody's creating their own code and so on afterwards, so things may become a little bit sketchy or so. But if you create a workflow everybody understands based on a fundament everybody is committed to, then there's no ambiguity in creating a proper planning, operation, and analysis. So all in all, this was the case. The idea is to reduce redundancies and also error-prone self-solutions by the science teams. And well, the idea or the bet was successful. SPICE is today used by anybody, by everybody in the space industry, whether it's NASA or ESA. the scientists and so on all use SPICE and its complex kernel structure to get a common ground. Now, SPICE is an abbreviation. Maybe some of you already are joking about the Dune movies or so, but it stands for spacecraft, planet, instrument, C-matrix events. Everything appears to be quite understandable except the C-matrix thingy, but we will talk about this a little bit later. And it's still actively being developed by the NAF and the Jet Propulsion Laboratory, or within the JPL. And it is currently developed officially in 4 different programming languages. I think it was C, Fortran, I forgot the other ones. And there's also an unofficial wrapper for Python. And this unofficial wrapper is also the fundament for our work, our live coding session in the next lecture. Now, the good thing is that with SPICE, it enables us to answer almost any geometric problem in the solar system. Like, for example, time conversion. Time is not trivial. Yeah? It's not like your clock where you have a certain time from some atomic clock and everything is fine. Time is very relative, and also spacecraft have also their own clock and so on. We'll talk about this in a moment. We need to also determine the positions, like, for example, where is the moon with respect to Earth, with respect to the sun, or so, to, for example, plan the missions properly, or also for the flybys. You want to have a flyby at Jupiter. Where is Jupiter exactly, so that you're not crashing into the planet or so. And also the orientation and pointing. Yeah, so you are having a flyby, or you observe, for example, Mars or even the Earth with some surveillance cameras, with some monitoring cameras or what have you. You really need to know where you're pointing at which direction. And if you're considering longer distances, so for example, for telescopes, you want to observe, let's say, Neptune as seen from Earth, then you have even to consider the light time. So the time the light needs to travel from this position to our position, and also correcting the relative movement of all the planets, like the observer position at Earth and Neptune. So things can become very, very complicated, and SPICE gives us this ground truth and also all the data handling and wrangling, so we do not have to be bothered by any complex self-made algorithm. Field of view considerations, the same thing, it applies here. And this is also where the C-matrix comes into. These are like matrices that determine more or less the camera settings, also field of view and so on. It's a more complex topic for a larger seminar, but today we will cover the, let's say, most basic things and also the coding session as well. Yeah. The other thing is also that we need also a ground truth for miscellaneous constants and properties. So for example, what is one astronomical unit? What is, for example, also the mass of the Earth, the mass of the sun, the gravitational constants, and what have you. The point is, these values, you can of course download them from the internet, but yeah, where do you take the most recent results? And if we commit to SPICE, then we can say, okay, all ground truth values are also within this toolkit that we can use later on. Here are some resources maybe for later. I can also easily switch maybe to my virtual desktop here with all the links. The links are provided in the description. And here you see, for example, the normal SPICE website with all the information. We have also here the SPICE toolkit in C with all the documentation. You can use the C documentation for the Python code. It's pretty straightforward. Most use RPs, the reference guide, and what have you. Something that is more related for, or where we take a look at next week. And then also the so-called kernel structure. Yeah, the kernels are the fundament. These are the building blocks, the Lego bricks, so to speak, for SPICE. And these SPICE, they contain all the information, the geometric information, the time information, what have you. We have to download them manually, and all the missions have the kernel. So you can even plot, for example, the Apollo missions if you want, the Cassini mission. And farther down, we have the generic kernels as well, where we have, for example, the different kernels for the planets and so on with very weird abbreviations. But we will talk about these abbreviations in a few minutes so that you know what is what. We go now to the science planning and operations to give you a real world experience or real world idea where these things apply. And first of all, we do some, we check some take a look at some plots to see how things are being managed. Because the idea is that in science, when you have a spacecraft for a few billions of dollars and you send it to space, then of course you want to maximize the scientific return. Some scientific, let's say purists would say, yeah, science is about finding the unknown, the thing we don't need the planning maybe, yeah, let's expect something that is completely unforeseen. But the thing is, for example, if you fly to Saturn and you fly, let's say, through one of the ice geysers of Enceladus, then of course the unknown is what is in this geyser. You don't know what's inside the moon, but you know, maybe you have to know the pointing and the direction your instrument needs to point so that you can obtain these unknown data. So it's not like a complete Wild West of science work. You really have to plan for these events. Otherwise, well, your observation time is completely wasted. And of course, we need to optimize it also for the different observation needs. Yeah. So for example, Cassini mission or other missions, they have not only one instrument, but dozens of instruments. And then you can also optimize the geometric configuration of all the instruments so that it's also optimized and maximized for everybody. Yeah. Sometimes you have a prime instrument that says, okay, for the next 12 hours, the requirements of this instrument are set as the most important one, and then the other ones are secondary. But even in this configuration, you can optimize these settings. And this leads, of course, finally to work out potential conflicts because, well, science is science, yes, but different science teams with different project owners, they are, of course, also interested in a political way to maximize the results of their own instrument, right? Because it's their small instrument baby. They want to have the best results of the entire mission. Yeah, of course, it's not like a conflict in a way that you have like two different instruments doing the same thing and then competing each other, but it's more like, yeah, a dust instrument, a camera instrument, or a plasma instrument or so. Everybody wants to maximize their scientific output. And of course, you have to work out the conflicts by not only maximizing, but optimizing between the different instruments. Last but not least is also to avoid the pointing mistakes. Yeah, you do not want to have a flyby at an asteroid and then completely miss the asteroid with your camera system. That would be a complete failure and also, yeah, a little bit shameful, so to speak. Not only avoiding pointing mistakes, but also avoiding conversion errors, because there was, for example, one mission, I think it was a Mars mission or so, I forgot the name, where it was, I think, NASA is computing everything in imperial units, in metric units, and some of the parts somebody was computing something in imperial units, and this led to the catastrophic failure of the instrument, so it actually burned in the Mars atmosphere and vanished. Yeah, basically what I just said, flybys, things are not repeatable. I think this underlines the statement. Let's consider some geometric configurations so that you understand how the things look like. So for example, here we have like a sun illuminating a planet, and then you have a satellite here in the lower left that is revolving around this object. You want to know which parts am I currently covering with the camera, what is the orientation of my satellite. And these are all the things that we can do in SPICE that we need to consider to optimize it, right? We need to also consider the size and the shape and the orientation of the object, not only from the satellite, but also from the object itself, because this is here a very perfect case of a ball sphere shaped thingy. But in our next session, we will have a look at some very weird objects, some shapes from asteroids and comets, where things are not that trivial, so to speak. After all, we will have a complete understanding what is the foundation of all the parts that need to be loaded to consider this instrumentation, pointing, properties, and so on. So this configuration on the left side that looks, let's say, as a small drawing, kind of simple, almost childish, contains a lot of complex information and mathematics, and try to figure things out in the solar system with the values you have at hand. It is really a humbling thing. We can also compute then also events. Yeah, we need to do it, like for example, an occultation. Yeah, this is maybe important. For example, if you want to point your instrument to Earth to receive radio transmission data or so, it's literally not working when you have something obstructing it. Like for example, if the satellite here is behind the planet and I don't know, Earth is somewhere here, then of course you cannot do it at all. And also other things like, for example, where is this satellite in a certain altitude? This is also important. We had this for Cassini when we were having a flyby at Enceladus. Of course, you do not want to crash into the moon, but you don't want to be too far away. You want to have the perfect spot to fly through this ice geysers, and this is also what has been done. So this can be computed. Or also when it's an object in front of another object. Yeah, for example, this could be interesting. For example, if you analyze, let's say, the atmosphere of Titan or so, and you want to know, okay, when is the sun having a perfect line with Titan and my spacecraft, so that I can, for example, analyze the atmosphere because then it's being illuminated by the sunlight. So this is also something we can compute. Or also you are at Mars and you want to analyze, for example, Olympus Mons, the tallest mountain of Mars. You need to know when it's visible, where it's visible, what's the orientation, where is my spacecraft, and how do I have to adjust my spacecraft to have a look at this particular spot. Now, in the last case, of course, light time is maybe not that important because you fly maybe, let's say, 5,000 kilometers above the surface or so. Yes, there's some effect of the light time, but considering the resolution or also the field of view of cameras, in such a case, it's maybe not that important anymore. Let's have a look at one of the particular instruments that I was also working on during my PhD, is the Cosmic Dust Analyzer. So what you see here is the Cassini spacecraft with all its instruments, and here we have CDA. It's around 0.5 meter in size. You see also here it's some kind of plate that was later also ejected in space because the instrument itself here on the right hand side looks a little bit, has an opening of this 0.5 meter, and it's made to detect cosmic particles. Cosmic particles in the size of a few micrometers. They are traveling kind of fast with several kilometers per second, so even dozens of kilometers per second. And here on the left side, we have a cross section of this instrument. And of course, it's a little bit complex, but yeah, try to stay with me how this thing works a little bit. So for example, we have here, let's consider only the blue particle. The blue particle is flying through the instrument with, let's say, 15 kilometers per second, and it passes first these 4 different grids. You see the grid mounting here. 2 are a little bit aligned. And in this aligned grid, in this QP channel, you can, for example, determine based on something called the rise time and also the plateau here, the velocity, speed of the particle, as well as also the mass. At some point, it flies through the instrument and hits at something called the chemical analyzer target, the CAT, which had a coating of, I think it was rhodium. Here, when the particle hits, it's like really smashing against the wall. And what happens is that this particle is completely destructed and is being ionized. And these different ions, they are charged particles, and they are then accelerated by around 1,000 volt to the multiplier. Before we go to the multiplier, beforehand it was flying through the ion collector QI with minus 350 volts. So you see here the QI, this is like a charge. And then the charge increases and then decreases afterwards because the ions were flying through the instrument, through the grid here. And based on the QI signal, you were also able to determine, the velocity, the mass of the particle and what have you. Now the multiplier itself, this is like a small time of flight spectrometer. So what does it mean? It means that especially particles with, like for example, hydrogen or the lighter particles, they reach the multiplier first. The heavier elements like oxygen and so on, they reach the instrument later, which means that we get some kind of comp structure here in the bottom right. And this comp structure reveals us the chemical composition of the particles. And that way we were able, for example, to not only determine the Cassini's environment, but also to determine the flux and the composition of interstellar dust. So particles that came from a different solar system into our solar system, and we were able to analyze several of these particles and the chemical composition. Now, the interstellar direction, just to let you know, this is a bird view of the solar system with all its neighbors and all the neighbors, how they are moving, and also the local dust cloud and gas cloud. And we are moving with respect to this cloud into a certain direction. And this direction is like a wind that is coming to us. Yeah, it contains gas and also dust particles. And these particles were particles that we measured. And how did we know it? Well, first of all, we know from previous instruments where this direction is. So the good thing is with SPICE, we know we can compute the direction where it's heading. Yeah, and then we know how to orientate the instrument to point into this direction. Now, the other thing also with SPICE is we can then also compute, for example, the expected velocity of particles in the Saturn system. Yeah, if you have a bound orbit around the Sun or Saturn, you only have, based on gravitational laws, a definition range of velocities that lead to a bound orbit. And if the velocity is way too fast and it's coming from the direction of the interstellar direction, then we know, or we have the indication that, well, this could be of interstellar origin. And this is what we did. So what we see here, for example, are the different particles as an asterisk. Yeah, and these are the interstellar particles, distance from Saturn in Saturn radii, and the dust velocity with respect to Saturn, and their velocity was way higher than the expected velocity for bound particles or even ejecting particles. Here's one of the time of flight spectra that I just was mentioning. In microseconds, from 0 to 5 microseconds, we see light particles are coming first, like for example C+, O+, and then later magnesium, aluminum, Si+, potassium, iron, and here at the end you see rhodium, which is not part of the particle, but it's also smashed out from the coating and then also being accelerated. So this rhodium peak here at the end, it's a very heavy element. It's also good for calibration purposes. So you know, rhodium is coming at the very end. So that way we can adjust and understand the spectrum a little bit better. Why? Well, because the spectrum also depends a little bit on the velocity and impact and so on of the particles. So the different peaks, they can also stretch and vary and shift. So the rhodium peak is very essential for this very task. Now, before we dive into SPICE, just one last words about the dust in the Saturnian system itself, where also SPICE is helping us to analyze its structure. And the thing is that, of course, particles like, for example, dust that are on a circular orbit around Saturn, yeah, this is a very schematic overview, they are revolving on a let's say circular orbit, and our spacecraft on a very elliptical orbit. So what happens is we have different velocity vectors. Yeah, the spacecraft is flying into one direction, and for example, the dust particles are coming from the side. Now, try to make the mental gymnastics of sitting in a train. Yeah, so you're sitting in a train and it's raining, there's no wind, this train is standing still. You see how the rain is coming down in vertical lines, right? And if the train starts to accelerate, we reach a certain travel velocity, we see that the raindrops are coming in an angled, in an angled trajectory, because, well, the velocity trajectory of the train and the raindrops need to be considered. And this is the same thing also here. So if we want to see where the particle is coming from, then we have to invert the vector of the spacecraft, and that way we get the velocity pointing vector of the measurement. And with this vector and with SPICE, we know then the velocity of the spacecraft in the Saturn-centric coordinate system, and we can compute back the velocity of the dust particle around the Saturnian system. And then with SPICE, even with SPICE, then we can, for example, compute the orbital elements of the particles. But we will talk about the orbital elements a little bit later. So long story short is, beside planning and operations, we use SPICE also after the observations for data scientific analysis. So as I just showed you with the case of the dust particles, for CDA, we have, something like we can determine the orbit definition range of impacting dust particles. So we have certain errors, right? We can also we can also determine the velocities of the particles and see if in a certain coordinate system, Saturnian or ecliptic coordinates, in the sun-centric coordinate system, we have particles with a velocity that are on an escaping path, which indicates that they are maybe interstellar. And then also we can derive, for example, coordinates from particles on a moon's surface. I just told you that we were flying along some moons like Enceladus or so, and these moons, like Enceladus has ice geysers, we measure these particles, and theoretically you can also map them back to the surface of the moon. Then you have a coordinate system there, and you can even do some mapping on the moon that is revolving around a planet that is revolving around the sun. So you see the complexity that is behind this topic. Last but not least, also for the dust guys, to determine also the density of the dust for different radii was also something that was being considered, and where SPICE is helping us because, well, the structure of SPICE helps us to determine where Cassini was. And we will talk about this now in the next part of this SPICE overview. Now, I think you have now an understanding and an idea why we use SPICE, what is the purpose of it. And I would suggest now that we take a look at a diagram that looks a little bit old, but it's still valid, and it's still the most recent workflow of SPICE. So try to ignore some things and try to focus on the red blob here. The red blob, which means that this is like your scientific program, planning program, or what have you. You want to determine velocities, altitudes, angles, and what have you. So the things that I was just showing you. So we have our own module, our own computational code, for example, to determine a density or so. And we have the SPICE modules that we need to determine this. For example, we need the position of Cassini, the position of the moons, the position of Saturn, and also the orientation of the instruments. And how do we do that? Well, SPICE is not only software, it is also has a fundament called SPICE kernels, some ancillary data that contain, for example, time conversion information, the positions of the planets, the position of the spacecraft, and so on. Yeah, and these are from some sources, like for example, from the mission control center that determines the position of the planets, or also from the spacecraft, and also some other more static information, like for example, how is in a Cassini, let's say Cassini coordinate system, the camera being orientated. Yeah, so what you have is basically a large setting of different files, and when you create your workflow or your program, SPICE is having a workflow that tries to go from a path A to a path B, and this contains a lot of different routines and also all the kernels, and this makes it also very robust and also very modular. And I would suggest to take a small example here in this case. We have, for example, Cassini observing Saturn. And now what happens is we have a lot of different SPICE kernels that we need. First of all, we need the position of Saturn with respect to the Sun or the solar system barycenter. Why the solar system barycenter? Well, consider the gravitational laws. We are not revolving around the Sun. We are revolving around a common gravitational barycenter. Yeah, and this barycenter is sometimes even outside the Sun, just to let you know. So we have some SPICE kernels that consider all the different effects. So we want to, for example, have the illumination of the Sun on Saturn. So what we have is we need the vector between the solar system barycenter and Saturn, and also the Sun to Saturn, but we go always the path with our central ground truth, which is the so-called, the solar system barycenter. So it's not like we have a kernel from the Sun to Saturn. We have probably more like a kernel from the SSB to the to Saturn, and from the SSB to the Sun, and the rest is simply vector addition, subtraction, and what have you. The same thing also for the spacecraft. We have also coordinates from the solar system barycenter to Cassini, and one to the Earth, and within the Earth also maybe to an antenna reference system. And the Earth, we know, has a certain orientation, shape, and also a coordinate system. And if we want, for example, to compute now how is the antenna aligned to the Earth and the camera aligned to Saturn, it's basically just walking along these different paths. Yeah, so we have, like, for example, the green ones are the paths that determine or provide the positions and the velocities. Now the red ones is more like the orientation and shape, yeah, and is also time dependent. This is indicated with red here, and also red for the spacecraft and for Saturn. And then we have also different reference frames, yeah. So Cassini has its own reference frame. The solar system has one, even the antenna on the Earth, and you can even determine your own artificial system. And then, of course, considering the geometric pointings, you have also then considered the light time between all these different players. And this is also what SPICE is doing. So what basically SPICE is doing, you make a simple request, and in the background you have different workflows or paths of workflows that try to figure out, for example, when is the camera pointing to Saturn with certain light conditions or so. So it sounds simple, but the maths behind, you can imagine, is very matrix focused and also very heavy, considering also the light time thing and also the time conversion, because time is very relative and also very dependent how fast you are, where you are, and what have you. Now, talking about this kernel data, I would like to go through the kernel data a little bit because, well, first of all, yeah, who provides these data are the spacecraft, mission control, operations, the instrument owners, for example, or the scientific community. You can even create your own kernels. This is nothing for the session next week, but for the larger tutorial, I would like to show where costume kernels will play a role. Later, I have a case where I created my own kernel to show you an actual use case where this might be of interest. Science organizations like the International Astronomical Union for all the constants and so on. And after all, we have then a common repository everybody commits to with kernels everybody understands if they read the documentation. So there is no ambiguous data. We have everything crystal clear in one repo. And this repo is something I already showed you, namely here. I showed it to you where I was giving you the insight of the different kernels. And here, when we go back, the parent directory, we have here the different missions and so on. And here for the generic kernels, we need to find, however, we have not to find it. We have to talk about the different namings of the kernels because kernels have different names. But believe me, we will understand all these different types just in a moment. So we start with the first kernel, and in total we have 10 different kernels. The first kernel is the SPK one. And the SPK is basically providing us the spacecraft and the planet kernel information, so for all relative positioning, velocities, and so on. But not only spacecraft, but spacecraft, planets, satellites, comets, asteroids, you name it. Yeah. This is the very first kernel type. So when we go back here, we see SPK. So we go there, and then we see, okay, the folder structure differentiates between the different objects. Let's go to planets, for example. And there we have some weird namings, DE432S, BSP, and part 1, part 2. Confusing, but thankfully we have a good documentation. We go to the summaries file, and there, for example, we have all the information that we need. Of course, you can say, hey, it's not a modern, super fancy, reactive dashboard or so. Yes, I agree. They rely on the good old text to have something that is hopefully reliable in the long run. And let's take, for example, DE432S.bsp that is also here. Yeah? This is a file that contains the Mercury barycenter with respect to the solar system barycenter, the Venus barycenter with respect to the solar system barycenter, and so on and so forth. Now we have here the Earth barycenter with respect to the solar system barycenter, and further down we see we have the Earth with respect to the Earth barycenter. So we can then, via the solar system barycenter, compute the position to the Earth, Earth barycenter, and then to the Earth. And we've also the Sun that is computed with respect to the solar system barycenter. Geez, I'm repeating myself. We have also the time interval here. So this kernel is valid from 1949, December 14th, to the mid of this century for the 2nd of January. So this kernel here is 432S. And then, for example, if we take a look at another one, like for example, this one here, part 2 of 431. So just keep in mind 431 and 432. We see a way longer time range until 17,000 years. And this should also hopefully reflect in the size of the particle of this file. So we have here 432S, around 10 megabytes, and part 2 of 431, 1.7 gigabytes. Of course, in modern computers, in the age of AI, this shouldn't bother us. Yeah, it simply loads into the RAM and you can perfectly execute everything. But yeah, why to keep things? Why to download the big files and not the small ones? Well, it's really up to you. Yeah, it really doesn't matter. I just check out what I really need, especially when I create my own Python library for others with a download functionality. Then downloading 10 megabytes is sometimes faster than 2 gigabytes, especially if people have a slow internet connection. So yeah, for your own work, you can do whatever you want, I would say. But when you create a library where you automatically download kernels, I would consider this fact just to be sure. Okay, the next one is the PCK kernel. Here we have the planet's orientation, size, and parameters, like, for example, what is the radius of the Earth, or what is the mass of the Earth, and so on. So this is the PCK kernel. So we can also go back here and have a look at the PCK. We have here the PCK. Let's go in there. And also here we have an AAA text file. And there we can have a look what we have here. And it's pretty much. So you have really to go through there with all the references to some papers and also the International Astronomical Union and so on. And now my microphone is obstructing my view, but for example, this one here, Mars ERU 2000 V1, a file that contains data only for Mars and its natural satellites. Orientation data in this file are identical to those in other files. Okay, cool. And we have also other information there. We have also information about the gravitational constant and time mass, like here in GMDE 442 TPC. Super confusing for now. You will say, okay, I will never handle this, but that's why we have our second session next week, where we go slowly through these things. Don't worry. IK is the instrument kernel, so something that, for example, the engineers are setting up. So you want to have to know the orientation of your instrument in the spacecraft. The CK kernel is, for example, for the instrument attitude. So, for example, it provides a certain reference frame. Then we have also the EK. This is like the event kernel. It's also differentiated in 3 parts, like science observations plan, observation instrument commands, and also some notebooks and so on. I never used that so far. Maybe I'm more like the data scientist, more on the science end. Maybe this is more used by the engineers. And then the frame kernel itself. So what is the reference frame we are moving in? Yeah, and this is something I will cover in a moment. So if you have never heard about coordinate systems, don't worry at all. We will get this covered. Yeah. And the most important thing is that we have fixed and dynamic or non-inertial frames. And the difference between these things is also something I will explain. So just keep this in mind, but I will give you a summary just in a second. What's ultra important is the leap second calculation table conversion. We will talk about this also in a few slides, because time conversion is a pain. Yeah, it's something you will never understand this. I will never understand this. Nobody understands it, I think. I don't know, maybe 2 people on this planet, but conversion between different time reference frames is so wild. It's really wild, but don't worry, we have a good overview slide in this regard. Now, speaking of time, each spacecraft has its own clock, like my smartwatch I have on my arm, gives me the time everybody is using, right? But spacecraft have their own clock with their own ticks, and they are using their own clock system, so to speak. Also something that we will use next time, although let's say it like this. I wrote it that it's not that common in science teams, but it changed over the last years. It's at least my personal perception. This is about the shape models of the objects. So, for example, you have maybe seen the different comets with their weird structures and so on. How can you generate these 3D models? And with the DSK part, you can do it. And this is something we will do next week, just to hook you for the next session. This is something we will do, and it's pretty cool to get an understanding and a feeling how these objects look like in space. Some additional meta information for the MCAR part, and that's basically it. So a lot of different kernels, I know, but in our session today and also in the coding part, we only need 3 kernels to get things done. And for our part next week, we'll also use the SPK part. But the good thing is we only need theoretically to conduct some research. We need only the 3 kernels here for very simple tasks, but we'll talk about this just in a moment. Let's go now to the individual kernel parts that I would like to cover. I may have seen a short break because I need a glass of water. Totally forgot about that. Very important for giving lectures to stay hydrated. Where was I? The leap second kernel. Yeah. I think this is pretty much the summary of this timed step. It is like the heartbeat of the solar system. Yeah. And it's defined 2006 by the EIU, and the, let's say, ground truth is a so-called barycentric dynamical time, TDB. And this TDB part is complex. Yeah. So don't be confused by this one. It is just having different colors to show you how this TDB is related to all the different time conversions and how. For example, what kind of function needs an leap second kernel or a spacecraft kernel or both, or what does not need a kernel at all. And as you can see, most things, they need a kernel. The thing is that we will also use kernels. We need kernels to, for example, convert a human readable time string into this TDB, into this barycentric dynamic time. The thing is that otherwise SPICE cannot really work. You do not have to understand this completely and fully, because this is something we will learn on the fly with the different Python codes. The next part is also less complex. Yeah, the PCK part, as I already said. For example, what is one astronomical unit? Yeah, of course, 150 million kilometers plus minus, but the true value, you will find values at Wikipedia, at the EIU, on other websites, blog posts, what have you. The ground truth is set by the International Astronomical Union. And ESA, NASA, and so on, they adapt these values, and these values are in the PCK kernels. So if you want to be 100% sure what you're doing, use these PCK kernels. This is like really the ground truth. And for example, we have here a function that I made a screenshot of a SPICE, using the SPICE kernel, for example, the function bot VCD or VRD, but let's go for VCD. It's a function you can also use in SPICE, yeah? SPICE.bot VCD. First, we have a number, 699. Now, this number corresponds to Saturn because NASA has some kind of catalog which relates all the objects to a number, and Saturn has 699. And this function says we want to obtain something from the kernel. We want to obtain, for example, the radii. Now you will say, wait a second, what kind of radii? I want to have the radius of Saturn. Yes, but we have 3 radii because for all different 3 axes, yeah, X and Y are probably the same, but into the Z direction, it's a little bit flatter because of the rotation of the planet. So that's why we need 3 values. And 3 is also something that gives SPICE the information, how many values do we expect as an output. So this is a little bit weird, like, hey, I just write radii, why do I have to provide the information? Well, this is how SPICE works, yeah, and you have to understand what you want to obtain. The 2 values here are the output values, and in radii we have then a vector of 3 entries with the X, Y, and Z values. We will have a look at this next week when we are doing our coding part. Just let me scroll a little bit. The next part is the reference frames coordinate system. And the question is always, is it the same thing? Well, yes and well, no. The thing is, and here's like the summary, and let me just read it because it makes perfectly sense. Because a reference frame sets the stage of a physical observation, and a coordinate system provides the mathematical language to describe what is happening on that stage. So the reference frame is the stage, and the stage has its people, its settings and objects on the stage, and the position where these people and the objects are, these positions are defined by the coordinates. Yeah, so the coordinates like x, y, z, but x, y, z makes only sense if you know with what is the reference, with what respect are we doing it. So let me take an example. My position is currently 0, 0, 1. Yeah, or 1, 1, 0. But these values doesn't mean anything if you don't know what's the reference system. Yeah, so let's say my position is, I don't know, 1, 0, 0. But the reference frame is the green screen behind me, and the 1 indicates 1 meter, and yeah, everything else is based on the center of my green screen. Then it makes sense because you know, okay, the reference frame is my green screen, and I am currently 1 meter away in X direction with respect to the green screen. Makes perfectly sense, right? And the same thing applies here as well. Now, for example, on the Earth's surface, yeah, we have then, for example, if we have a coordinate system that is defined on the surface itself, it would, and you walk a few meters away, it will have small numbers. But if you put the reference frame to the core of the Earth, then anywhere you are, at least you have over 6,000 kilometers as the distance vector, because you have to go from the core to the surface first before anything happens. And this is what it shows here in this reference frame. We see X, Y, and Z. We have the right hand rule, so X is the thumb, Y is the pointing finger, and Z is the middle finger showing into the top. And in Spice, we need to define only two vectors. Doesn't matter, it's f as x or y or z and y. The third one is simply orthogonal to the others. So in Spice, you only need to define 2 of them. And in this reference frame, you can use the Cartesian coordinates, spherical coordinates. It really doesn't matter at all. Now, the thing is, what kind of reference frames do we have? Now, for example, we have here the equatorial coordinate system, the J2000, where we have our plane of our Earth inclined by 23 degrees with respect to the ecliptic plane. And the ecliptic plane is the plane, you know, take a table, take a sun in the center of the table, and let the Earth roll around the sun. This imaginary plane is the ecliptic plane. Yeah, and our plane, like our equator, is inclined by 23.4 degrees with respect to this ecliptic plane. And these matrix computations, these complex things, they are being conducted by SPI, so you do not have to worry about this at all, which is pretty cool. We will take a look at the software, I think, so I will make a cut just in a few moments, and I think it makes also sense for my lecture. We have also other coordinate systems, like here, very extra, I don't know what the name was, it's the ICRF frame that is, for example, defined by the orientation to almost 300 extragalactic sources. And then, yeah, you can define the XYZ plane. Also, the ecliptic coordinate system is something we have. It's, for example, determined by the vernal equinox. But yeah, let's talk this. I would say let's talk about it now. So I'm switching now the screens, and I hope I will not forget to make the cut when I'm making the video. Now, here we have a planetarium software. It's called Stellarium. It's perfect. It's open source. You can really use it. We have here the sun, and you see when I'm recording it, it's now, actually it's lunchtime, but I'm not hungry yet, so it's fine. And we can increase it to the evening hours of today. Let's go, or tomorrow. Perfect. Now we have here our stars and everything. Yeah, looks pretty nice. Let's turn on the constellation. We have here Orion. Maybe you know Orion. And now if we turn on the equatorial grid, this is the grid of our Earth, let's say. So here where is Polaris, yeah, the North Star, and everything revolves around the sort of line of this of the polar axis of the Earth. So everything revolves here. The equator is at 0 degrees. Let's see if we see it. Yep, there it is. This is like the sky equator, so to speak. Now what we can do is we can turn on the ecliptic plane, for example. Like, no, we can't. We can only do the azimuthal. I have to do something else. Anyway, just to give you an idea that you can do this, you can also, I think, turn on the extragalactic grid as well, but let's not play around too much here. I just wanted to show you how the projection of this reference frame looks like, and within this reference frame we can set now the different coordinates. Anyway, let's go back to our slide before I'm really losing track. The equatorial ecliptic J2000 is something that we will use for all the spacecraft, especially for interplanetary missions. Yeah, so we have something that is like the vernal equinox. So at the vernal equinox, our Earth, we take the Earth and we look with the X direction to the Sun. Yeah, with the Z direction, we look perpendicular to the ecliptic plane. And the Y vector is simply the right-hand rule. I hope I did this correctly. Yeah. And that way we define our reference frame. And the good thing about the reference frame is it's not Earth-centric. The reference frame can be set anywhere, and especially the ecliptic J2000. And it's commonly used to have it in a solar system barycenter or the Sun. Yeah. So coordinate systems can be translated. Now, as you see already in the Stellarium software, like a sky map, we have here the, I think this is now the equatorial, no, is this the equatorial one? No, this ecliptic one, yeah, ecliptic. Then along the 0 line, we have the planets more or less, and also the Sun, because not all planets are on the ecliptic plane. They vary a little bit, so it looks almost perfectly. Now, if we change it here to the equatorial plane, to our Earth-centric, where we have the 23 degrees inclination, then this ecliptic plane changes its shape a little bit. We have a transformation between both coordinate systems. Looks trivial in Cartesian coordinates, but if you have a sky map, it's less trivial. And here we have then our ecliptic plane that is then having this almost sinus shape, and the planets and also the moon, not the moon, the Sun, they are along this ecliptic plane, more or less. Now, another thing I want to show you, this is like an inertial coordinate system, which means that it's completely time invariant. It doesn't matter whether we look at it now or in 200 years. Ecliptic J2000 is ecliptic J2000. So why bothering about non-inertial coordinate systems? This is something I want to show you now for another scientific domain, namely meteor research. Now what you see here are the Geminids. I just made in my YouTube channel another video about these. This is a meteor stream that has its peak, I think, now in a few days, between the 13th and the 14th of December. And these, if they are hitting Earth, it appears like they're coming from a certain direction, the so-called radiant. Like, you know, when you're driving with your car while it's snowing, the snow particles also seem to come from the front. And like this little line of thought to infinity is the radiant. And if we plot all the radiants on the sky map, we see the different sources. We see the Geminids, the Perseids, and so on. So where the different meteor streams are coming from. Yeah, here it's also mapped with the impacting velocity. So we see a lot of different blobs in the night sky, and we can say, hey, cool, in J2000 this looks pretty nice. And J2000 is non-inertial it's an inertial reference frame. So why should we bother about an inertial reference frame? For this, I would like to go a little bit back to this here. Imagine a coordinate system where the x direction corresponds to the velocity vector of the Earth. So x is not time independent, it varies with the movement of the Earth. The coordinate system, if you just look, can you see me here? I don't know if I'm tall enough. Yeah. So the coordinate system, like this, is moving along the orbit like this. So that's changing its position, its orientation all the time. Now, cosmic dust has certain areas where it's coming from, like for example the meteors, but also our Earth is flying through the dust, and it looks like from this flight direction it could be that there are particular more than from other directions. And this is what you can do with the non-inertial coordinate system. Now, if we have the non-inertial system, let's have a look here. This is how it looks like. This is how the different regions appear. We have certain regions, so-called the sporadics, like here in the center, with 72 kilometers per second, and others that are way slower coming from another direction. For example, from behind the Earth or from the side or so, but in the flight direction, we have the highest impacts. And this is pretty interesting because here in this part, we don't have any meteors because these are data from a visual instrument, and during the daytime it's pretty difficult to see meteors, so this part is pretty dark. So this is like one use case of using a non-inertial reference frame. Last but not least, I would like to gather things a little bit up, what we had now, a deep dive into 3 kernels, the LSK, the PCK, and the frame kernels. And the frame kernels, well, with these 3 things, we can already do some spice work. Yeah, we could determine movement with the Keplerian elements. Yeah, Keplerian elements, maybe you have heard about it. We have 6 degrees of freedom, so we need 6 Keplerian elements plus a 7th one to determine the position. And these are, for example, the semi-major axis, the argument of periapsis, and so on. You don't have to know it for now. Maybe it's a little bit too much for this session. We can talk about this later. More important is that to determine the shape and orientation and the position of a particle along this orbit, for example, around the sun, we have all 3 kernels to work with. Yeah, and there's a function, for example, here it's called conics, that computes us the state, so the XYZ coordinate based on the orbital elements. We can also do it the other way around. And for this, we simply need nothing more than a time frame, because time is always the key. Spice doesn't work at all without time. Yes, it does, but not for the geometric stuff. We need a reference frame on the very right, and in the center we need also the for example, the mass of the sun or the gravitational constant. And with that way, we can then, for example, take orbital elements and compute this so-called state vector, so x, y, z, and the corresponding velocities, or take the state vector and compute the orbital elements. So with these 3 kernels, we can actually conduct a lot of Cassini science, the dust science, because, well, we know already where we measured the particles. Okay, we don't have the orientation for now, but theoretically, if I provide you the state vectors of all the dust particles, you can simply compute then the orbital elements, for example, also around Saturn, and see how the dust behaves around this ring planet. Now for the SPK, I already mentioned it. SPK is basically responsible for the movement and the movement parts. So we have like the solar system barycenter, and then we have the kernels with respect to the solar system barycenter and also others, and then everything else, the orientation, the pointing, and so on, is basically based on vector computations between these different entities. However, we have to consider the speed of light, and the speed of light is really real, but it's really difficult to grasp sometimes, because we don't have only the speed of light, we have also our own movement. So for example, do you see me here? Yeah, we have, like, for example, Neptune, we have, for example, the Earth. Now we want to observe the Earth or have the right pointing of the telescope. While we observe Neptune is moving, but we are also moving. So when we want to have a certain configuration of moons, we have to take into consideration our own movement. We have to consider the time when we want to measure the certain event, and also the light time between Neptune and Earth. Have fun creating your own algorithm, but SPICE provides us these things. And this is the cool thing, because this is a very simple example. Yeah, so we have here The blue one is, for example, the planet we observe. Yeah, it looks like a bowling ball, but this should be a planet. And we have here a black star on the left side. And this is how we would, for example, see it. However, the true one is the red one because it already rotated a little bit. So we have to consider these effects. Otherwise, it is a little bit off grid. Yeah, if we have a very narrow field of view, then maybe our planet is not anymore in the camera system, but only a fraction of it. That would be really bothersome. And if we, for example, want to have a certain event, like for example, the moon is hiding, being covered by the planet, we also need to consider the right time when it's happening. And this right time needs to consider the speed of light. So if you don't do this, we get into a lot of trouble. Now the correction factor we have is, first of all, none, which doesn't correct for anything. Everything is like a as-is state, considering an infinite speed of light and no correction. But if we use the so-called light time plus stellar aberration correction, LT plus S, you will see this in the SPICE documentation, we will get then the correct values. Yeah, so the mandatory for any computations that are time critical, this is pretty important. Otherwise, it will mess things up, to be honest. Yeah, this is like what's to be considered for the SPK kernels. And these 4 kernels plus the shape kernel is something we will take a look at in the next session next week. I would like to give you a short insight what I did with Python and with SPICE. Like for example, here we have the Rosetta start of all the different flybys, and you see how the velocity is increasing, flybys to the different asteroids. I know it's a very simple animation, but hey, better than nothing, I would say. And we see the third flyby at Earth, and then going to this very high ecliptic orbit, then reaching to the comet Churyumov-Gerasimenko, and then landing on it in, I think it was November 2014. So this is what you can do with SPICE, and also, for example, with Destiny Plus, you know, in the University of Stuttgart, people are building on an instrument. These are very old kernels that was estimating that it's already launched, but it didn't launch. It's a mission that is heading for Phaeton. So Phaeton is an active asteroid that's responsible for the Geminids, and it's also planned to have a flyby there. I think it was a little bit postponed, but flybys are still possible. Phaeton is coming very closely all the time. And the configuration allows us to still plan for a few years later. So also this has been done with Python and a library called VisVis that I found already back in 2012. A very small library, but pretty impressive what you can do with just a few clicks. Not for interactive work or something for your website, but to generate nice small videos. Last of us, let's go back to our browser. As I said, we have here something called SpiceyPy, and SpiceyPy is like a wrapper for SPICE. As I said, SPICE provides it in 4 different languages. C, Fortran, I don't know, I think MATLAB or Java or something like that, I don't know. But Python is not officially being supported. But a cool guy called Andrew Annex said, well, let's port everything into Python. And he actually did it. And the installation, if you're familiar with Python, is pretty straightforward with pip, for example, or conda. If you're not familiar with that, do not worry at all. You do not have to have any fulfill any requirements in regard of installation for next week. We will talk about it just in a moment, but here are just some documentations and also some common issues, but there are no major ones. So you can simply do it. Here's also an example with the Cassini position example. So also examples here with the Cassini movement, for example. And also some other readings, but hey, you have here also my lecture. Now last thing is I wanted to go back to our generic kernels. I also provide the link in the description. We have here now the frame kernels, for example, for the planets, a Earth coordinate system where you can go through and see what's going on there. We have, for example, the leap second kernel, and I can only tell you this NAF 0012.tls is currently the most common leap seconds kernel. So actually you always need this one here. It contains all the information and the file looks pretty simple though. But yeah, it's really important to load it, otherwise things will not run. PCK we were also covering. We have some constants here and there. For the SPK, we were going for the planets. You can also take a look at the Lagrange points, the comets and asteroids, what have you. And even for stars, we have something, but I think this is a pretty small database. Yeah, I don't know. You have to check this. I never used this one. Now we can go back to the parent directory. For example, go to the Cassini part. We have here the kernel directory, C kernels, F kernels, LSK, PCK, and so on. Now, if we go to the SPK kernel part, we have here all the different kernels and also our documentation. Wow, this is a pretty big database. Let's go through AA_summary. No, they don't have it. README they have at least. Cool. And you see also there are also some generic kernels, so not only from the Cassini, but everything you need for Cassini. And these things are sometimes a little bit more complex, so you have to go through the naming convention. Like here, it's the structure as the delivery date, then V or T. What does it mean? Yeah, for different here, file version, optional, only usable and applicable. Okay, cool. And T, the T part is not T, but it has two endings, P or R. P is the predicted trajectory, so the one that has been, for example, computed by NASA to see where we wanted to fly. And R is the reconstructed one, so the actual one. So R is something you want to use for your analysis, and since Cassini is no more since September 2017, you can always use the R part. Then we have some kind of description here. Yeah, I don't know, let's go through here. The starting event and end event. What is being covered. So for example, I have here an example. The binary file is delivered at this date, so September 1st, 2024. It is the first version, A, of a predicted kernel, P, covering from 2004, so this one here, day 192 to 2005, day 58. Yeah, you may ask, why not put everything in once? Well, it has probably historical reasons, yeah? So these things, they grow organically, and sometimes you cannot really foresee how things change, considering that Cassini started back in the 90s. All in all, we have almost 90 minutes covered. Hooray. Next time we go into the live coding part. This will be our next session. And now for the university people, I set different requirements how to work. Now here, this is a public YouTube channel, so I'm more free in what I want to do. If you want to follow the coding session next time, the coding session here online will be longer than in the lecture, because in the lecture I simply show the code and get into the discussion. Here we will go through line by line. We will write the code. Yeah, I'm not having a live session because I'm not a streamer, but we will have a very long session to get these things covered. And for this, I simply ask you to get a Google account, a Gmail account, because we will use everything. We will use Google Colab. And Colab is also like a Jupyter notebook, like a notebook that runs in a Google Cloud, and it's perfectly sufficient for our use cases, and it's also easy to use. And I would suggest to use this one for our next session. So please prepare everything until then. For my students, you know what to do, what are the requirements to do it in a university context. But I hope you learned something. I hope it was enough. Again, it was just the surface scratching of this topic. And thanks for listening, and until next time.